Okay. So, we have constructed the Lebesgue measure completely now. So, we have Rn, we have the Lebesgue sigma algebra on Rn and the Lebesgue measure on Rn, and we looked at some finer properties of the measurable sets. Today we will first look at some properties, some invariance properties of the Lebesgue measure itself, and then we will see that any Lebesgue set can be approximated by Borel set very closely. In fact, the Lebesgue sigma algebra is the completion of the Borel sigma algebra with respect to the Lebesgue measure. So, that is what we will do in the first session. Then we will go on to look at non-measurable sets and things like that. So, we will start with some invariance properties of the Lebesgue measure. Okay. So, recall we have the space Rn, we have the Lebesgue sigma algebra and the Lebesgue measure. So, also recall that we have the Borel sigma algebra B of Rn, and that is of course contained in the Lebesgue sigma algebra, we know that, okay, and which is of course contained in the power set. And yesterday I had mentioned that the inclusions are strict, okay. So, we will construct examples to show that these inclusions are strict. So, we start with some invariance properties of the Lebesgue measure. Invariance properties of Lebesgue measure. On Rn. So, this gives an idea about how the Lebesgue measure interacts with various natural operations on Rn. So, the first one is translation invariant. Translation invariance. So, let's just look at translation. So, what is translation? Translation is if I take a set E, let us say subset of Rn. So, we are not assuming it will be measurable now, and some vector h in Rn, then we can define E plus h. So, this is translating E by h. So, how is this defined? This is defined to be all x plus h where x belongs to E. So, we are simply translating the set. So, if the set E is like this, and depending on where h is, you will get E plus h to be somewhere here of the same shape, okay. So, when I drew, the shape will change, but shape changed, but it is exactly the same. So, an easy example would be on the real line. So, let us look at the interval 0 1 and translate. So, let us say this is E translated by a number 2. So, let us see what is E plus 2 is. So, E plus 2 will be all x plus 2 where x belongs to E, right. E is the closed interval 0 1. When I add 2 to it, I am going to get the interval 2 to 3. So, this is simply translating E to this interval. So, you translate this by 2, right. And when you translate, of course, you see that the length of the interval does not change, and this is true for cubes as well in Rn. So, when you translate, the measure should not change, okay. So, that is the first assertion. So, let us prove that. So, let me write this as a result. These are easy results, but these are very important results as well. So, if I take a measurable set L of Rn, E in a Lebesgue set, then and okay. So, you fix a vector in Rn, fix a vector h in Rn, then first of all E plus h is also measurable, that is one assertion, and the measure does not change. The measure of E plus h, the translated set, and the measure of E are same. So, to say m of E plus h, one needs to know that E plus h is in L of Rn, okay. So, that is the first assertion, and then we say that the measures are same. Well, proof is very simple, but let's do this in a slightly elaborate manner, because the other invariance properties will be of the similar kind. So, first thing is, let us recall what is the measure. So M of E is M star of E, right? So it is the outer measure of E. Only thing is E is, if E is in the Lebesgue sigma algebra, we say M of E. Okay. So let us keep that in mind, which is equal to the infimum of various quantities which we have seen so many times by now, mod Qj, j equal to 1 to infinity, Qj are closed cubes, closed or open does not really matter, closed cubes, and more importantly E is covered by Qj, right, and then you take the infimum of these quantities. Well, it is very easy to see that. So for M star is defined on the power set of Rn. So M star of E is defined for every set E. We don't need to bother about any measurability properties. So if you look at E plus H and M star of that, well, what is this? This is of course infimum of various quantities. So I am not going to write this. So the only condition is E plus H is contained in whatever union you are taking. Okay. Well, so how does it look like? So let us say E is here and E plus H is here. So if I have cubes covering E like this, and I translate E to get E plus H, if I translate these cubes, I will get a cover for E plus H, right. And similarly, if I translate back by minus H, I will get a cover for E. So covers for E plus H can be translated to covers for E and vice versa. So what I want to say is, if I have E contained in union of Qj, j equal to 1 to infinity, Qj are cubes. So if you translate a cube, you are going to get another cube, right. So if I translate this by some vector, I am going to get something similar. So that is a cube. Then, well, you can say if and only if E plus H is covered by the cubes translated, right. So these are also cubes, Qj plus H, cubes. So because of that, M star of E plus H is equal to infimum of summation j equal to 1 to infinity volume of all those Qj which cover H. So you translate them. So now you get a cover for E plus H such that E is contained in union Qj, j equal to 1 to infinity. Okay. But what is Qj plus H? The volume of Qj plus H, volume of Qj plus H is same as volume of Qj, right. If you translate, you do not change the volume. So look at the easy example. If I have an interval of length 1, I translate it to any place I want, I will still get a interval of length 1. So if I translate, I am not going to change the volume of the cube, right. If I have a square in R2, I translate it, I am going to get the same square, but the area, the square position will change, but the area is going to be the same. So this is simply mod Qj. So this is same as infimum of j equal to 1 to infinity mod Qj, where E is contained in union j equal to 1 to infinity Qj, where Qj are cubes. But this is the definition of M star of E. Okay. So this is a trivial computation we have done, but it shows that M star of E plus H is same as M star of E. So M star is translation invariant. If you translate the set, you are not going to change the value of M star. Okay. So but it does not prove that E plus H is measurable, right. So we need to show that as well. So suppose E is measurable. Suppose E is measurable. Okay. What does that mean? So for every epsilon positive, there exists an open set O such that such that the outer measure of O minus E is less than epsilon. This is what measurability means. So, what we have is E, a set here, and some open set around it, right, that is my O. I am trying to prove that E plus H is measurable, right. So, I simply translate this open set O by H. So, I will get O plus H, right, and whatever is the difference, remember the difference is simply translated by H, right. So, m star of O plus H is a set minus E plus H, okay. Well, what is this? This is m star of O minus E plus H. Well, you need to verify this is a trivial thing, but remember the minus here is the set theoretic minus. So, let me write it down for A and B. Suppose I have two sets A and B. I look at A minus B, right. What is A minus B? That is A intersection B complement, okay. Now, A plus H as a set minus B plus H, right, it is another set. Well, what will this be? Okay, so, this is A plus H by definition intersected with B plus H whole complement, okay. So, you need to check that this is actually equal to A intersection B complement translated by H, okay. So, that's sort of trivial from the pictures, but you can write down a proof if you want. Okay, so, go back to m star of O plus H minus E plus H, that is m star of O minus E plus H, which is equal to, so we just proved that m star is translation invariant. So, that is same as m star of O minus E, which I know is less than epsilon, and the fact that O plus H is open, if I translate an open set, I am going to get an open set. So, what we have proved just now is given an epsilon, there is an open set O plus H such that m star of O plus H minus E plus H is less than epsilon. So, that implies that the set E plus H is also measurable. E plus H is measurable. And so, m star of E plus H is m of E plus H, right, that is simply the definition. So, m of E plus H, that makes sense to write m of something, that something has to be a measurable set. This is equal to, I know it is equal to m star of E because m star is trivially invariant under translation, and this is equal to m E. This is precisely the result we asserted here, right. So, let me, yeah. So, we claim that E plus H is measurable and the measures are same. So, Lebesgue measure is translation invariant. If I translate something, I am not going to change the measure of the set. So, that is the first property we have seen. Second property, second invariance, this is with respect to dilation. Okay, so what is dilation? So, you start with take some positive quantity delta greater than 0 and you multiply by delta. So, you are looking at the map from Rn to Rn, okay, x going to delta x, right, that makes sense. So, remember x is a tuple x1, x2, etc. xn, delta x would be you multiply all of them delta x1, delta x2, usual vector space operations, right, this one. And this you can do for sets, right. If I take a set E contained in Rn, I can define delta times E to be delta times x, where x belongs to E, just like what we did for translation. Now, we want to say a similar result hold for dilation. Of course, Lebesgue measure will not preserve dilation, that is easy to see. So, let's look at some example to guess what should be the answer. So, let us take the interval 0 1 in R, let us multiply it by 4. Okay. So, multiply by, let's say, 4. So I will get, if I multiply by 4, I am going to get, so I'll draw it here, 0 to 4, right. That is the interval. So if this is E, this would be 4E. What is the Lebesgue measure of E? That is 1, because it is an interval. So the length is 1. And if I look at the measure of 4E, I am getting 4 times measure of E. So whatever you are multiplying by, it comes out. Okay. But let us look at R2 and look at another example. So let us take this unit unit square 0 1 here. Okay. So this is my set E. If I multiply it with delta, okay, so let delta be positive and we multiply this with delta. So how will delta E look like? Well, that is also a square. It is cornered at 0 0, of course, but these coordinates become delta 0, delta delta and 0 delta. Okay. What is measure of E? The 2-dimensional Lebesgue measure of E, this is 1, right. This is the area of this square. Measure of delta E, right, this is delta E. Measure of delta E is the area of the square. So I have delta here, I have delta here. So that is delta square into measure of E. So this time, so instead of 4 here I have delta square, it is not delta, right, because the 2 depends on the dimension. Similarly, if you go to R3, you will see that delta cube comes out. Okay. So the result we want to state is result, okay, let E be a measurable set L of Rn and delta be positive, then, well, first of all, delta E is measurable, so that we can talk about its measure, and L of Rn, and the measure of delta E is actually equal to delta to the n. So the n comes from the dimension of Rn, right, times measure of E. That is what happens. Okay. So let us prove this. So as earlier, we will look at m star of something and see how multiplication by delta acts on it, or the effect of multiplication by delta on m star. Okay. So let's go back to general set A, subset of Rn. M star of A by definition is the infimum, right. We have seen this so many times now, mod Qj, j equal to 1 to infinity, A is contained in union Qj. Now what is m star of delta A? Well, this is infimum of some collection, right. What are those collections? So just like what we did earlier, we see that A is contained in union Qj, j equal to 1 to infinity, if and only if delta A is contained in union j equal to 1 to infinity delta Qj. So all you have to do is to dilate the cubes accordingly to cover delta A. So this would be infimum of summation j equal to 1 to infinity modulus delta Qj, right, where Qj's cover A, right. So A is contained in union Qj, j equal to 1 to infinity. So you take any such cover, multiply by delta, you will get a cover of delta A. You take any cover of delta A, divide by delta, you will get a cover of A. Okay. So that is why this is true. So the collection of cubes have to be the same essentially, apart from multiplication by delta. Well, but what is this? Well, for cubes it is easy to compute. So let's see Q. If I take a cube Q, okay, so cube, say let us say closed cube, this of course is a product of intervals a1 b1, a2 b2, etc., A and Bn, right. So, it looks like something like this in R2. You multiply by delta, well, of course, you are going to multiply each of them, A1 B1 cross delta A2 delta B2, delta is positive, remember, cross delta AN delta Bn. So, what is the volume of delta Q? Well, you will look at the product of the sides, right. So, that is delta Bj minus delta Aj, j equal to 1 to n. So, from each component the delta comes, right. Each side has got dilated by delta. So, the side changes by delta, and from each component you get delta. So, this is delta to the n times whatever remains is the measure of Q. So, for cubes this is trivial, and that is why it becomes true for all other sets as well. Okay. So, this from here I will get that this is equal to infimum of, I will get delta to the n outside, summation j equal to 1 to infinity mod qj, and A is contained in union qj, right, j equal to 1 to infinity. But delta to the n will come out as a positive quantity, and you are taking the infimum of the remaining, which is simply delta to the n times measure of E, measure of A, m star of A, right, the outer measure of A. So, we apply all this to the result we want to prove. So, we started with E belonging to L of Rn. Okay. Again, we do not know what happens to delta E, okay, but we know that the m star, the outer measure of delta E, is delta n to the m star of E. This we know, okay, and this we know, well, let me write it for general set so that we can use it for different sets. Okay. So, A and A, this we know. Now, E is measurable implies for every epsilon positive there exists an open set O such that the measure of O minus E is less than epsilon, this we know. Well, what should we do to get an open set around delta E? Well, we will look at delta O, right. So, delta times O is open, okay, and m star of delta O minus delta E, well, what is this? This is m star of, so again trivial verification to be checked is this. So, what did we use? We use that delta A minus delta B, well, this is delta A intersected with delta B whole complement, this is nothing but delta times A intersection B complement. So, this is what you have to check, this is a trivial thing, equal to delta times A minus B. So, that is what we have used, and we know that m star, when you dilate m star has the property that delta to the n comes out. So, a measure of O minus E, which is less than delta to the n times epsilon, okay. That is also enough, right. So, if you want to be very precise, for every epsilon there exists an open set O such that m star of O minus E is less than epsilon by delta to the n. You can start with that. So, that will give me delta O minus delta E is delta n times this is equal to epsilon, okay. So, this inequality implies that delta times E is measurable, and of course, if it is measurable, then we know that m star of delta E, well, this is actually m of delta E equal to delta to the n times m of E, this we know, right, because that is a property of m star. So, that proves this result. So, this result is proved. So, Lebesgue measure is translation invariant. With respect to dilation, it gives me a factor of delta to the n, okay, that is expected. And well, there is one more result. So, I will not prove this in as much details as we just did, but because this is much more easy. 3, reflection. Well, what is reflection? Reflection is the map x going to minus x. So, this is a map from Rn to Rn. Okay. So, the result we want to state is, suppose E belongs to L of Rn, then its reflection is minus E. Minus E equal to, well, what is this? This is minus x, where x belongs to E. That is the reflection. So, in the case of real line, suppose I take an interval here, let us say a b, this is my set E, then minus E will be minus b to minus a, right. This would be minus E, and of course the length does not change, right. If I take a cube q in Rn, cube, then minus q is also a cube, right. This is also a cube. More importantly, minus q has the same side length. So, the volume will be the same, and so m star will respect this, right. So, m star will not change when you take the negative of minus of q. So, m star of E and m star of minus E will be same. Okay. So, easy to verify. So, I will leave it to you, easy to verify that m star of E is same as m star of minus E. So, this is because any cube q and its negative minus q, whatever it means, will have the same volume, okay. And so, when you take the infimum, it is not going to change. So, any cover of E, you can take minus of that will get a cover of minus E, and the corresponding quantities are same. So, because of this, if E is measurable, then of course, so for every epsilon positive, there exists an open set O such that m star of O minus E is less than epsilon, right. So, you can change everything to minus E now. So, this would imply that you look at minus of O is open set, this is an open set, and m star of minus of O minus E. So, remember there are two minuses here, the slanted minus is the set theoretic minus, right. So, if you look at minus A minus B, well, this is minus A intersection minus B whole complement, and you prove that this is actually equal to A minus B minus of that, right. Okay. So, this is equal to m star of minus of O minus E, and we have seen that when you take minus, nothing happens to m star. So, that is m star of O minus E, which is less than epsilon, which is precisely the statement that minus E is also measurable. Implies minus E belongs to L of Rn. So, I started with E in L of Rn, I have minus E in L of Rn, and of course, m star of E and m star of minus E are same. So, m of E and m of minus E are same. Okay, so let me stop with some remarks. We have just seen three invariance properties of the Lebesgue measure. It is translation invariant. With respect to dilation, we have a certain different kind of invariance, and it is reflection invariance. You will notice that these the last two examples, the dilation and the reflection, these are linear maps from Rn to Rn, and so you can ask the question, how does the Lebesgue measure deal with or how does it behave with linear transformations on Rn. So, a general result we will state later and prove so, because there are certain things to be established before we can state the result. If you translate or if you apply a linear transformation to a measurable set, we have to prove that it is measurable, and its volume or its Lebesgue measure would be the determinant of the linear transformation times the measure of the original set, and that is precisely what you have seen in the case of multiplication by delta. So, multiplication by delta is a linear transformation whose determinant is delta to the n, and x going to minus x is another linear transformation whose determinant is 1. Okay. So, that does not show up here. Okay. So, we will stop here, continue.